As you can see, they are like not transparent at all. You can see they have like a blur transparency. They are stretchable. You can press them, and they can recover their shape. And because of its high ionic content, they can conduct electricity up to 3 millisiemens per square centimeters. Yeah.
So the primary material you're using here is?
Oh yeah, they are made of gelatin.
Gelatin.
Gelatin and other technical solvents, so they are full biodegradable.
Yes, like everything we do here is about bio-based ingredients or something that is already in the food industry or the pharmaceutical industry.
Yeah, so that helps a lot.
Yeah, so one of the main advantages in the future will be that you can dispose of them. It's very easy. Just put it in a pot and just hope those nutrients go to a plant or something like that. Yeah. Because on a large scale, it will be more engineering.
So you have the gelatin. Do you functionalize this material with some materials?
We functionalize the cellulose with biotechnic solvents. It's the main constituent of the gel, the solvent.
Yeah.
Yeah, Ali doesn't know anything about biotechnic solvents.
Oh yeah.
So you can say a few words about it.
Yeah, you can say what kind of things are.
Okay. Instead of using water, we use what we call biotechnic solvents, which are mixtures of hydrogen bond donors and hydrogen bond acceptors. Like in this case, we have choline chloride and ethylene glycol. And the mixture is prepared in a molar proportion of 2:1. And they are actually have a sample here. As you can see, this is
monomer. Is that what it is? Monomer solution?
No, it's the solvent itself.
Solvent itself.
Yep.
Okay.
Yes, as you can see, it has a low viscosity, so this is the main reason which it can conduct electricity.
I see.
Other solvents, like the one prepared with urea and choline chloride, are not conductive enough.
So when you functionalize it with the solvents evaporate, doesn't it? Or you keep solvent in it?
The advantage of using this compared to water is that these materials don't get evaporate.
I see. So you basically entrap the solvent.
It's kind of ionic liquid.
Okay.
If you're looking for a parent more well known, it's an ionic liquid. But it's an ionic liquid composed of natural ingredients.
Correct.
Yes. And it's not really an ionic liquid in the sense of only cations and only anions. There's some mixtures with neutral molecules. But it's also a complex, so it's a very homogeneous mixture. And so that's the real advantage. Yeah.
Cool. So can you tell us also a little bit about application, about how they envision to utilize this technology?
Yes, we have previously designed strain sensors where once you stretch them or you push them, they produce a change in its resistivity. So you can measure it and use it as a wearable device in order to measure motion or to detect an electrical signal. Yeah, we are using these materials for those applications.
So you can make maybe interlinked sort of devices for the shoes or socks, for example. Is this something that you're envisioning? Or some bandage, maybe?
The disadvantage of these materials is that they have a low melting temperature because it's made of gelatin. So we can use them in lower temperatures. We can still measure change in resistivity at low temperatures. And the plan is to keep using the same solvents, but maybe change the polymer, in this case gelatin, for a material which has a higher melting point. But the main goal is to work and improve the sensing and wearable devices technology. Yeah.
Wearable devices.
Yeah.
Cool. Awesome.
Also, the material has birefringent properties. Once when you stretch it, you can have an optical response. So
it's something that's pretty useful, isn't it?
Yeah. So you can have dual response with optical and electrical signals. Yeah.
So you feel that you're learning a lot in this project?
Yes.
So polymer chemistry.
Polymer chemistry, material science, also a lot of things. Yeah.
Awesome.
Green chemistry.
Green chemistry.
Green chemistry, yeah. It's a very big thing.
Saul won this scholarship for a summer camp with the ACS in chemistry.
Oh, this is very nice.
No, Denver.
Okay.
Denver. Okay. Colorado.
Yeah, in Colorado. Actually, the last week was the annual summer school.
Oh yes. So you were there for some time.
Yeah, I was there the previous year.
the highest point in the United States, isn't it, Denver? Highest altitude city.
Yeah, yeah. A lot of people like to do hiking.
Yeah.
Yeah. The mountains there.
And what's your name?
Saul.
Saul.
Yeah.
And your surname?
What?
Your surname?
Carrasco Saavedra.
Oh, cool. Thank you very much.
Carrasco dash you know?
Specifically for proteins, we haven't really gotten to the part where we are analyzing them in complex liquid, like plasma or something like that, but that's the aim. Our RGLs have been proven to have a very good surge response in Raman spectroscopy. And they're made of cellulose and gold nanoparticles.
Okay. So you
have some examples?
Yes.
I have some collapsed ones here. These ones have already.
So you're using
analyzed.
all natural materials, cellulose.
Yeah.
Yeah.
And they have gold nanoparticles, which is, well, the inorganic part of them, which I think we take some out of the desiccator. Here, like this kind of sponge-like substrates in order to collapse them with the analyte. The thing is that they have hydrogen bonds between them, and when you add the analyte in water, they collapse, and so they have a higher concentration of hotspots between the nanoparticles. And they have a very good surge response. That's what we're evaluating here.
Okay, so you're embedding gold nanoparticles in cellulose-based materials, correct?
Yeah. Exactly.
And what's the application of this technology?
We're trying to use them to diagnose and follow the progress of diseases with markers, biological markers.
So which sort of diseases do you envision to
Okay, so
utilize?
we haven't really gotten that far, but we could say, for example, inflammatory diseases that have markers in blood that could be easily detected.
Yeah, so how does this, for example, differ from materials like nitrocellulose in the market that people combine nanoparticles with?
The thing is that the cellulose is functionalized with carboxylic acids on its surface, so it allows the formation of hydrogen bonds between the nanocrystals, because this is cellulose, nanocrystalline cellulose.
Okay, nanocrystalline cellulose.
Yeah, there is no chemical cross linking between the cellulose nanocrystals.
Yeah.
So it's just holding all together by hydrogen bonds. So it is
Hydrogen
very
bonds.
prone to collapse once you
I
add
see,
the water.
I see. And you're using Raman spectroscopy, is that
Yeah.
right? So it's very, very successful method, isn't it? It's used around the world for many
Yes,
applications.
yeah. So Kaori is about to start a stay, a short stay in Germany. What is the name of this institute?
It's the Leibniz Institute of Photonics and photonics.
Photonics technology.
Yeah, photonics technology.
Right.
So she's gonna work with an expert in CERS in Germany with sweat.
Oh, with sweat samples.
Yes.
Yeah.
That's really, really cool. I think nowadays there's increasing applications, as you know, from I think Joe Wang. I think published lots of papers. You may know him in UC San Diego on
Yes,
like
sure.
wearable devices
Yes.
combined with sweat samples and so on.
Those papers were about electrochemical
Correct,
devices, right?
correct.
So it's a very complex, fancy devices, right? So here is very simple. It's just collapsing the sample because of the sample is contained in a liquid. And we were talking with this colleague, Mania. What is his name? What's her name? Dana. We were talking with Dana, and the thing is, there is not much research about proteins in sweat because it is very difficult to detect. So once it gets to the surface of the skin, there's a lot of enzymes that degrade the proteins. So the sweat evaporates very quickly.
Yeah.
So the chance of getting samples is horrible.
Yeah.
So this will be a real.
Yeah, we also spend some time in trying to look at sweat and whether it can be useful biomarker. One of the ways that to extract the sweat is using a stimulant, a
Yes.
chemical stimulant. I think that's one of the challenges in this area, but it's widely available. If you join our talk tomorrow, I will also talk very briefly about sweat technology and the sensors that we are developing for athletes, so special people who are doing sports.
Yep.
So we have a startup company who specializes in looking at sodium ions in sweat samples and they are correlating with those sort of concentration values with the dehydration status of an athlete.
Nice.
So it will be really something to.
She's doing a master here right now. So Salul is just right now starting the PhD.
Yeah.
But about the PhD project, we were thinking about iontophoresis.
Yeah, reverse iontophoresis. Yeah, it's a very, very big thing, and a lot of people are looking to this really cool area. Yeah. So,
Yeah.
thank you very much.
You're welcome.
And what's your name?
Kaori.
Kaori. And your surname?
Sanchez. Carrillo.
Thank you very much.
You're welcome.
So what is this, for instance?
I'm doing an essay about determination of proteins with the Bradford method. What I'm doing here is that I prepare 1 milliliter of my hydrogel that is made of cellulose, well, nanocrystalline cellulose, and I am going to determine what the quantity of the proteins that my hydrogel absorbs, and I need to incubate this for 48 hours, and this is the method that I use with cells.
So what is this hydrogel good for? What do you do with the hydrogel?
What we are looking for, well, what it really does, it's that we cultivate cells in 3 dimensions instead of 2 dimensions that it's what it's usually to the cell culture. So this is the project. This is what the project is about.
So applications are in determining protein concentrations for in tissue engineering. Is that right? Or bioreactors or something like? Is that right?
It's more for 3D cell culture.
3D cell culture.
We try to study what is the scaffold do to the cells and how the mechanical properties of this modify its morphology.
So yeah, so this work is in collaboration with Carla, Yuki. So she's a nanotoxicologist, so she needs a really good substrate to try the toxicity of several particles. So one of the main drawbacks of the current methods is that they culture the cells onto a slide to the cultures. So we are trying to improve that to a 3D, so the cells there are more similar to a tissue. So she can have a really good idea of the real toxicity of nanomaterials.
Cool. So from the collection of the projects that I've seen here, it seems like the focus of this laboratory is to design unique and novel substrates that could be utilized, and polymeric materials in particularly, for a wide range of applications in sensing and tissue engineering, maybe possibly drug delivery as well even.
Yes.
Is that right?
Definitely.
Yeah.
So I think, we had a talk with this Misael Silva. So he's what is his? He works with Merck. So he came here to give us a talk about innovation and how it is necessary to change the mindset of we as a scientist, just to, instead of trying to search for a niche application of the science that we are already doing, we need to change a little bit the science just to fit to the needs of the industry. If that is what we want to do, and it is really difficult because like there is a lot of lacks of facilities. So we need to have something in between of a doc application of our papers or research, and just trying to really solve real problems outside. This is hard. But,
yeah, I think a lot of academics nowadays, they're realizing the importance of commercialization. I think once you come to a stage in your career that you would like to explore maybe product creation, and I think your collaboration in Merck is very, very important. And also what I've seen in your laboratory is that you use very common materials, commercial materials. I think this is very helpful in terms of getting the things to creating a product.
Yes, definitely. So the first thing we faced, the first problem we faced, it was about feedstock. reliability of the feedstock. Different batches have different properties, so that was a problem. So, and working with natural or bio-source material, that is critical. So yeah, so we're trying to work with renowned brands that use well characterized materials to work.
Yeah. So one of the startup companies that a friend of mine has focuses on gelatin production. So where he didn't have a lot of resources. So one of the things he thought is that maybe he can produce gelatin at a very high purity level for research applications. So he started a company called Zeta Matrix, and I think they recently received a large investment. Even though the idea may sound very simple around the use of just the manufacturing of gelatin at a high purity level at a low cost could be very, very helpful for the industry as well.
Yes, yes. I think that the main problem here in our position is to combine the duties of a professor with a scientist that is only focused into industrial development. So that is, we have to manage between different phases of a scientist, and that has also an impact of the time that you have to pursue one of those goals.
Correct. Possibly they are also expecting you guys to produce intellectual property, like maybe patent applications.
Yeah, and in that case, we have a good support from our university. They have their own intellectual property department. Of course, we both have to learn a lot about the process because it's not easy. The path for every project is different. So, for instance, we had a project with the Bank of Mexico just to develop some inks for.
Security.
For security, yes, for security stamps in the bills. And we had a lot of trouble just getting the paper done, the paperwork done, because of, who is going to own the intellectual property, who's going to profit with if that scales to the production. And so, yes, of course, there's a lot of troubles here in Mexico because everything is about bureaucracy. But it can be done. It can be done. It's just a matter of knocking on the right doors.
Sure. Thank you very much for sharing your research with us. Thank you.
Thank you, Oli.
Thank you.
Here we have two CVD systems. This is chemical vapor deposition, where we grow these to be semiconductors, mainly transitional metal like covalents. So we grow from molybdenum to tungsten disulfide all the way to rhenium disulfide. So what we can do is, if we can cover like a large spectral range going from the red to the infrared. So rhenium disulfide, the gap is around 1.5 electrons. So these are like really basic
equipment.
CVD equipment, because this is atmospheric CVD. So what we have is just a furnace, a carrier gas, and that's it. So if you find the good parameters, temperature, time, and gas carrier lots, so you end up having these monolayers of these semiconductors. And what's interesting also is that you have, these are, when they are in the monolayer high configuration, you have direct bandgap semiconductors. So, so this is what we can do. So we have the growth section here, and then what we are working on is to fabricate devices. So what we have here in the other section is this is a laser direct writer, where what we can do here is just we put resist, we define the patterns, contacts, to put contacts on top of the crystals, and finally what we have here is the characterization. So from the growth to fabrication, finally the electrical characterization.
Electrical characterization.
Electrical and optoelectronic characterization, because we have a prep station here, but we can also, I mean, I have a fiber, so you can plug in into the scope, so you can inject.
Spectroscopic characterization?
No, just you can. It's optoelectronic characterization. So what we do is we excite the devices with different wavelength, different wavelengths, so we can have the spectral response from the devices. Right. And in the last, I have to say, 2 months, we have used, we have used this homemade
laser scribe.
Laser grinder.
Right.
So this is just you have a UV laser and a XY galvanometer. So what we do is, we play with the position of the laser, so you can write on top of it. And what we have discovered is that if you take cotton scotch, right? So this is like insulating.
Oh
stuff.
yeah.
And then when you insulate, when you play with the laser, it becomes conductive.
I see.
So it's the so-called laser-induced graphene. And we have double-checked this on Raman, and we have confirmed that it is actually graphene. So.
Right. So is there an oxidation in the process when you shine laser light?
Yes.
So you produce graphene oxide or something?
Right.
Right. Yeah.
Right. Okay. Yes. So this is something that we think that it has great potential, because I mean, with all the new staff members here, so we want to go towards a different different direction, and such a way that we can create synergies, interesting synergies to do high quality research. And I think with Eden, Gonzalo, and the new guys coming, I think maybe we have a chat.
There can be graphene oxide sensors as well for applications of electrochemical sensors.
Exactly.
Considered.
Yeah. Actually, I think it's reduced graphene oxide because with the same laser you can also reduce the material. So at the same time you will have reduced graphene oxide.
Right. True. Yeah. So this is something we have done. We have there's plenty of ideas. Sometimes again we have to find a good collaboration, to make different stuff, more complicated things. We can do something here, but then we have to reach out some guys to do complementary stuff.
Low budget science, high impact science.
Exactly.
That's our
this is
our strategy.
Our I mean, we need basic ideas, but very good ideas to make this happen.
Pretty novel.
Yes. So I'm still in tenure track. So this is the Extreme Hunger Games. That's you have so the starting budget here is 0. Right. 0 pesos, 0 whatever, and this has come from writing the first year a lot of proposals, and eventually I got the opportunity to grab a grant from here, and then you start because the prop station was abandoned. Like there was this researcher who had this prop station, so I just looking around from different labs, I just grabbed whatever the people didn't use, and you build this lab from scratch. And once you build it, then you have to make it work, right? Exactly. And yes, one of the advantages here in Mexico is that you don't have to pay students.
Don't have to.
You don't have to.
Don't have to. Yeah.
They usually, when they get accepted in a master program or a PhD program, they have access to money. There's a special grant for these students, so they pay. So this is something which is cool.
This is the very good part of science in Mexico. Actually, I was reviewing
grant from a European country, and half of the budget was devoted to salaries, let's say. And here it is already covered because government is paying this part.
Yeah. Cool.
Right.
Awesome. Thank you very much.
I mean, my pleasure.
Thank you. Cool.
Jonathan, and well, here in the lab we study different phenomena, mostly biological. We use cells to study their mechanical behavior using this device, these optical tweezers, and you can.
It's great. I'm very familiar with optical tweezers.
Are you?
Yes, I am.
Okay.
Yeah.
So we're developing it from scratch.
Yeah. Must
So
be a lot
we
of
don't have
work.
enough money to buy.
This is
Yeah. I understand. Yeah.
And as you say, in development, one of my colleagues is actually working with it. It's part of her PhD. So, what else?
So what's your
Yeah.
what grade are you? Where are you studying?
I'm
PhD, master's,
starting my PhD,
Mhm.
and I will be studying in the optical tweezers. There's a phenomenon called optical binding. So I'm studying the optical binding of a large number of particles in this device.
Right. So you will be using laser light, correct? To control. And which laser light do you choose?
It's near infrared.
1064.
1064 is in near infrared region. Okay. And are you utilizing the positive or negative fields specifically in the to control particles?
What? Excuse me?
Like the particles in the negative or positive regions of the electromagnetic wave?
I'm not sure I understand the positive or negative region of the electromagnetic wave.
So the focal point specifically, so you're focusing on a focal point because some of them can, if you focus light, it can repel the particles or it can trap the particles, right?
Okay, yes, it depends on the...
Awesome. So you're building it yourself. I think it's very rewarding, in my opinion, to build it yourself because most people buy it and they don't really understand how the device works.
Yes.
So it's a good idea to build it. Also, it makes it more publishable because if you buy it yourself.
Yes, of course, and we can add some features that makes the thing publishable.
Yeah, exactly.
And the student, well, Eden, she is in charge of the development. She's doing a PhD in engineering, so that makes sense. She learns a lot on developing all this from scratch. We have problems like electronics, of course. Not only light, not only optics.
Yeah.
And this we are going to this optical tweezer system, install it in the confocal microscope. So we're going to do optical trapping together with confocal. Our application is to, as Jonathan said, measure the mechanical properties of cells, different kinds of cells, under different conditions. The properties of the cell membrane.
Mm-hmm.
That's what we're doing here.
I will study the effect of the laser, of the optical tweezers, on a cellular membrane, and we want to study what happens when the laser is in the cellular, and investigate if there are different mechanisms in the cellular.
So yes, he is going to be charged with. Well, there is a strange effect that we noticed when lighting with it was a 810 nanometer infrared laser on the cell membranes of fibroblasts. We measured that with Luke. The fluidity of the membrane increased, and it made it molecules move faster. We measured that with FRAP technique, fluorescence recovery after photobleaching. But we came on lectures. There might be some effects due to the production of ROS, reactive oxygen species.
Right.
Okay, and we're oxide. There is some kind of oxidation that might itself modify the properties of the membrane. So Edgar is going to conduct a number of experiments to try and see if that is correct. So for example, we're going to repeat the experiments, putting some antioxidant, or with doing different kind of measurements, and we'll see what happens. So that's his PhD. So
yeah.
No, that's his PhD. His master's degree.
Master's.
Yeah, and we'll see what is going to produce. Perhaps he's going to go to PhD with the same subject. We don't know. We'll see. But you have to learn how to culture cells.
So it's a big challenge.
Yeah.
Are you a physicist yourself, or?
Yes, he's.
Yeah.
But he can do. I mean, he can do it. Of course.
Big challenge.
Well, I did it. I'm a physicist too, so and I managed to not to kill my cells. So
it's a very rewarding experience to learn about.
Yes, of course. I mean, that's just what we were talking about. We in the group, it is good to be each of us know a little bit of all the fields. For example, our specialist in cell culture, Laura, she is going to be in Slovenia for 2 months. So we will need someone to take over the cell culture, and you will do that.
Cool. Thank you very much for your time.
You're very welcome.
Yeah, thank you. And what are your names, just very quickly?
Jonathan.
And your surname?
Surname apellido. Lopez.
Okay, and your son?
Edgar Campos.
Yeah, and this is Luz Maria's lab. It's the chair of our department. No sé, a lo mejor está acá en su oficina. She's the chair of the other department, of engineering department, and she is Poromija, her lab. So,
Sounds good.
So she does a lot of biochemistry things. Hola chicos.
Hola.
Hi guys. This is Dr. Ali.
Hi everyone.
Hi.
And it's our guest for the seminar for tomorrow. And I'm going to give just a few explanations from the lab.
Cool.
Maybe later Luz is going to introduce Ali to all of you. Okay. Those are Luz students. So come here. This, well, you know all the stuff for that. And this is one of, this is the first room that I use. It's plenty small, but we do temperature here. And this is one equipment that I split now because we are going to change this. This is a flow cytometer.
Yeah.
And with this is plenty useful for toxicology. Yeah, so this, I earned this equipment when I was in Ensenada, and then
You were able to bring it?
Yeah.
I heard from your colleagues some of them had challenges and they were not able to bring their equipment.
Yeah, I was very lucky because this cost like $300,000.
Yeah.
So for us it's plenty.
It's
I don't know
yeah.
for you maybe
expensive.
it's
So it's expensive.
but
yeah.
it's expensive for
Yeah.
us. Yeah. So
Cool.
And here is the Centro Pro. Cycle culture room is, we have the devices for the hood and the incubator and microscopy. So here, now the incubator is not working, but now in the other lab I can show you the cell culture.
So when you carry out your sort of cytotoxicity assays, you use any ISO standards in general? So there are several standards, isn't it?
Yes, that's true. And that the OICD?
Yes.
Yeah, we use a standard for the
standard
ISO,
system.
And so also sometimes when it's not a standard, because of that, we modify the test.
Right.
And then we
perform it.
Yeah.
So what I've seen in the past is that a lot of people who are working in tissue engineering or cell biology, and they just carry out experiments in their own sort of way. So, and very few laboratories in fact follow standards, like ISO standards, that are applicable to commercialization of products. Is that right?
Yeah, is that right? And one of the main constraints is that we don't have a nanomaterial which can be considered as a standard, as a gold standard. So there is no way to compare the effects of your material with others, no? Because even though they could be synthesized based on, for example, silver, no? Silver nanoparticles, but the techniques and the raw materials are different, so, and also the sizes. So also one thing important is that when you review the papers, then the way that the authors report the toxicity, it's so is diverse.
Yeah.
It's nanomoles, concentration, micrograms per milliliter, number of nanoparticles. So there is no standard way to report the toxicity. So this is a constraint to compare the others, and also there is no standard material to compare the toxicity. For example, if in cancer, if you want to compare the toxicity of a drug, there is a first-line drug. Right. You know? And also the standard for that.
It's already there.
Yeah, but for nanomaterials are not. It's not. So that is the one of the constraints of nanotoxicology.
Cool. So in your experience, obviously you work with maybe a wide range of nanoparticles, graphene maybe, even carbon nanotubes, is that right?
I didn't test graphene, but I test carbon dots and nanotubes. Nanotubes. Yes.
So what's your opinion about their commercialization for in vivo applications?
Well, is that it's kind of difficult because it depends upon the concentration and the dose. So mostly you can test that, or the results pointed out that they are very toxic. Yeah. But I think there is a window of applications when safety could be achieved. Yeah. But nevertheless, this window is very it's very difficult to obtain because the nanomaterials are so different. So, for example, Andres is working with graphene. Yeah. So his nanomaterials is going to be different from the commercials.
Yeah. So one good example can be an MRI contrasting agents that are injected prior to MRI procedure.
For gadolinium, for example.
Correct. Yeah. Yes. And in general, they have been proven to be very safe and cleared from the body. But not always, that's the case.
Yeah, not always. But additional to that is that upconversion nanoparticles. I have been working with upconversion nanoparticles, downconversion nanoparticles, and all the nanoparticles in medicine made of lantanates, rare earths, gadolinium, ytterbium, and so. And they are very safe. Right. They don't have any toxicity at all. And henotoxicity is also not present in that. So I think they are very, very useful for contrast agents.
Cool. Yeah, so one of the challenges I know from my personal experience is that my father, he went to have his MRI and he was injected some of these contrasting agents. Yes. And when he came back right after MRI, his lymph nodes, one of them started swelling. Yes. And one of the things first thing that came to my mind is, this nanoparticle is probably aggregated in the lymph node and maybe causing inflammation. Yes. And then he had
it was injected with the nanoparticles or with the...
Yeah, so intravenous injection of particles. And this produces effects. He had to have a surgery to have it removed, his lymph nodes.
Wow. Yeah. Yeah, that's a problem because if you see the results, in vitro results and in vivo results, the in vivo results are all made in rats and mice. So there is no proofs that in humans going to be different, no?
Yeah, could be.
It could be different, but it also it matters of the dose.
Yeah, exactly.
The dose is something that we are not like widespread concern about the to report the dose in a universal way.
Exactly.
This is the main constraint, that we don't have a standardization way to report the toxicity, no concentration, no?
Right.
And there's no standard for comparison.
So, are there at the moment a lot of agents in vivo that are utilized for in vivo sort of injection that consists of non-organic materials, inorganic materials?
I would say, yeah, for contrast or in general?
In general, yeah.
Yeah, I think all nanoparticles are also very used for tumor and cancer cells.
Yeah, so photothermal ablation.
Yes.
Or as a photosensitizer purposes, correct?
Photosensitizers. Also, the virus-like particles are one of the main nanomaterials that is going to be really useful, I think,
right.
so, because they are proved to be safe and they can carry drugs and molecules.
Correct.
So they came from plants, from virus that infect plants. So I think those like nanoparticles are going to be widespread in the future.
It's great to know. Thank you very much. Are we going to see another lab?
Yes. Well, I don't know if your colleagues or someone is gonna see this. Is not a standard lab. It's not.
That's okay.
We are under the rules here.
It's for me personal.
Okay. Well, we call that Nanotox lab. This is our lab.
This is the logo.
This is our This is the logo. This is a mice, and this is a cell, and those are the nanoparticles that are
I see, it's really pretty. You designed this yourself?
I got the idea and someone designed it for me.
It's really nice.
And here are the nanoparticles getting inside the cells and affecting the DNA maybe. No?
Cool.
So we work with mice and we work with human cells.
Awesome.
So I have also tattoos for science.
Ah, can we have a look?
Yeah.
So can you explain us what we are seeing?
This is Maya. This is like a yin yang, but this is personal. This is that means God. But this is a book, Erlenmeyer flask, see, with nanoparticles inside, and a double DNA chain.
Yes.
Yeah, this is the DNA, and this is a micropipette, and those are nanoparticles. And these are Erlenmeyer mattress with a neuron. This is the serotonin, a nano capsule, drug, and this is an atom.
I see. Yeah. Cool.
Oh, my nephew did this.
She's a tattoo artist,
yes.
Your nephew.
Yeah.
I see. Wow.
Yeah.
Wow.
Yeah, I got this 2 weeks ago.
Oh, just 2 weeks ago.
Yeah, this one.
This one.
Yeah.
So you had this before this bit?
1 year ago.
1 year ago.
When I come here, I made this
cool.
like a celebration.
This is really nice.
And I made this because my nephew was sick, and he got a stroke.
I'm sorry to hear that.
Yeah, so he was very bad, and then he recovers and made that.
Professional tattoo artist? Yeah, sounds good. This is related to my talk actually tomorrow. I will be talking about tattoos as well a little bit.
Oh, okay.
Tattoos as sensors.
I'm the only researcher here who has
we have tattoos. Yeah, usually researchers don't have it.
No. Well, Nanotox Lab. These are our social media, Nanotox Lab.
Yeah.
And those are here. Some students, some very well concentrated students. No, it's like she's Anaí and she's Ellie, and both are doing the postgraduate studies. Ellie is doing the PhD and Anaí is doing the mastership. So they follow me here. So
nice to meet you.
Yeah. So maybe they can tell you.
Maybe you can say a few things. Yeah.
Yeah. I don't know if you want, who wants to explain, or maybe show him the cells. Yeah. So you want to see cells?
We can have a look. Yeah. Sounds good.
So Ellie is going to explain it.
Yeah, go ahead.
Que vayas.
Que le digas.
Introduce yourself.
Well, Jessica, would you like to speak my PhD project?
Everything. Just talk about whatever you like to talk about.
Okay. We are designing a scaffold of bacterial nanocellulose and nanorods. So in this image, you can see the bacterial nanocellulose native, and this is the chemical modification of the nanocellulose with carboxyl axis, and then we could introduce the nanorods in the scaffold for biosensor application. This is my nanorod.
Okay. So explain us what you're seeing there. Is it gold particles or what is it exactly?
Yeah, nanorods particles.
Nanorods.
Yeah.
Okay. And are they gold?
Yeah.
They're gold.
Gold nanorods.
Gold nanorods. Okay. And so what are their sizes?
The design is a scaffold.
And what are the sizes of the particles?
Okay. 50 nanometers.
50 nanometers. Okay.
And the fiber diameter is 31 nanometers.
Okay,
Yeah.
so excellent. So that's
Yeah.
great.
And this is for the growing cells, mammalian cells, in the surface or in the pores of the bacterial nanocellulose.
Right, so you're trying to grow some type of cells in scaffold, but at the same time use these nanoparticles as sensors, right?
Yeah.
And what sort of biomarkers do you wish to sense?
We have had a perfect of the different genes, for example, the bacterial nanocellulose, and then the growing of the cell in the surface, and we can detect metabolites of the cells. For example, with the cells had a differentiation of the other type of the cell by Raman.
Okay,
Yeah.
so you would like to utilize a Raman system to characterize it. Mm-hmm.
Yeah.
Okay.
And this is, you can check the mammalian cells
Mm-hmm.
that we have growing in the scaffold.
Cool.
You can see in this part.
Okay, let me have a look. What's up? Yeah, I can see it. So these are we seeing also nanoparticles or these are cells only?
Only mammalian cells.
On mammalian cells. And which cells are we talking about here? Which mammalian cells?
Okay.
Am I going to be able to capture this? Ah, I think I can capture it as well. Which type of mammalian cells are we talking about here? Fibroblasts, okay. So specific fibroblasts, cool. So let's have a look at it. I can actually capture it, it's really good. Oh, that's excellent.
That's good.
It's really good. Cool.
The design of hydrogels too as scaffolds with gold nanoparticles as spheres and rods too. Then look here, I have nanoparticles as spherical shape, yeah, as a spherical form, and then I have here some nanorods, gold nanorods. So these two materials I embed in the synthesis of the hydrogels and looks like this. This is my hydrogel. Then I put this to dry for some days and looks like this. Right. So now I can cut some slides and put these slides on the cell culture plate to put on the surface some cells and looks if this can have an adhesive
properties
yeah. Too, so these cells can grow on the surface.
Cool. So these particles are gold nanoparticles and they're red, right? What,
yes.
Are we seeing it at very low concentration? Slightly red?
Yeah, it's a low concentration.
So you're using very low concentrations.
Yes.
And so you're embedding this particle. And what is your hydrogels made of?
My hydrogel.
What is the material you use for hydrogel?
Alginate.
Alginate.
Yes.
Okay. Okay, so after you have integrated the particles in your alginate, what do you do with this? Do you use also Raman, for example, or another method?
No, only microscopy.
Okay, so you're looking at microscope. Are you looking at the behavior of cells, or what are you exactly observing?
First, I have to observe if the gold nanoparticles are on the hydrogel, embed on the hydrogel, and then with the cells on the surface, I can look if these cells are surviving on the top of the hydrogel.
So is this a new methodology that you're trying to experiment with as compared to, let's say, fluorescent live dead cell assays? Is that slightly different? So can you tell us the difference? How it differs from live dead cell assays or cell viability assays?
I think the main goal of analysis project is that use reactive oxygen species as a inductor of cell growing.
Right.
So the plan is that use the scaffold with the gold nanoparticles, compare the shape and the aspect ratio with the induction of the reactive oxygen species as a promoter of growth.
Right. Yeah. So it's some type of reactive oxygen species sensor.
Yes.
Is that right?
Yes.
Yeah. So yeah, currently I've seen some fluorescent sort of assays in the market as well.
Yeah,
right?
that could be. Yeah.
But you are trying to already integrate it within the hydrogel matrix for tissue engineering applications. Is that right?
Yes. That's why I this research involving the fibroblast cells, fibroblast cells, for the engineering tissue.
Tissue engineering applications. Cool. Thank you very much. And what's your name?
Anai.
And what's your surname?
What?
What's your surname?
Anai Lezama.
Okay. And what's your name and surname?
Elizabeth Mali.
Very nice to meet you. Thank you very much. Cool.